is a place there. Over there, yes.
Thank you so much.
Your neck will be stiff afterwards, but
Yeah,
anyway.
but better than standing, maybe. I don't know. Okay, I think we are more or less ready. And if I have the okay from the cameraman, I can talk. Yes. Well, welcome to the second Science Café of 2019. No, yes, no, oh my God, it's not, of the autumn season, at least. Well, because some of you are new, this is an event that we organize since 5 years. We, meaning the University of Turku, and specifically the Theoretical Physics Department, together with Tula, who is over there, who had the idea of the Science Café with me, and with Boris. Well, Science Café is usually an occasion to learn something that is a topic that is science-based, science-related, and as you know, today is a very important topic, global climate change, and it's structured in a way that we will first listen to our speaker. I'm introducing it in a moment, for about 40 minutes, half an hour, 40 minutes, or 45 minutes, after which we have a question and answer session, and then you can still approach him and ask him questions in Finnish if you don't want to ask in English in front of the public. But normally, the Science Café is let's say, famous for the friendly atmosphere, and everyone is encouraged to participate to the discussion. So we had our first Science Café of the autumn season about a month ago, and this was about quantum technologies, and then we celebrated the 5th year anniversary of Science Café, but today is another celebration, and the celebration is the 50th Science Café. So this is the 50th Science Café, and I'm very, very happy to have you all here and to celebrate with us, and I'm extremely happy also because we have a very, very honorable speaker here, that is Professor Jukka Käyhkö. It's very different from an Italian to pronounce the surname. It has a lot of difficulties are there. From the Department of Geography and Geology of the University of Turku. And I thank you already in advance for accepting to be our guest and to talk about such an important topic, global climate change.
Thank you, Sabrina. Where should I stand so that everyone sees it? I mean, I'm always in front of someone. What if I'm here? Would this work? Yep, oops. Okay. I have plenty of things that I would like to discuss with you. But first I will introduce some topics, and as the time is running, I will start now, if that's fine. Okay? And normally I allow questions and comments during the... so if you have a burning question in your mind, do that, but perhaps we then can discuss afterwards. We can scroll through the slides afterwards if you want to see some specific diagram afterwards, for example. Okay, today's topics, I'm trying to cover these. We are first asking, is the climate changing or warming? Then what causes the change? Is it anthropogenic or could it be natural? How does the future look like for the climate? And then we probably have to also consider how does the future look like to our society. I think that's the crucial issue here. And what should and what can be done regarding that. And I'm afraid that I have to say that I don't have an answer to the last question. But perhaps in this audience, there is so much wisdom that we can create something new. So, say 10 years ago, there were lots of skeptics or denialists who said that climate change is nonsense, that it's not happening. And I think today the voice is somewhat smaller now. You don't hear it much. But as scientists, we always have to also consider the possibility of us being wrong. I mean, it would be very sort of aristocratic or in an ivory tower to say that we know everything. We don't know everything about climate and climate change. But there is a good reason for us to believe that we understand enough so that we can argue some things. But let's start with from the bottom line, is the climate changing as far as we can tell? So let's look at the observations, what we can see. And let's start here in Turku. Unfortunately, this illustration is in Finnish, but I suppose everyone knows those crucial words. So this is Turku. And our annual mean temperature is 5.7 degrees in Turku. Approximately 6 degrees, in other words. That's the annual mean temperature in Turku. In January or February, which are the coldest months, it's about -5 degrees. And in summertime, in July or August, we have some 16 degrees, the monthly average. But the annual average is about 6. And here we now have the time frame from 1960 all the way to 2000, and I think this is 18, the last full year that we have in record. And the red bars here show temperatures that are above the average of this 1985-2010 mean. Because when we talk about climate, we talk about a 30-year period. Not 10, not 20, not 50, but 30-year period is an internationally agreed period for climate. Okay. And this is now the newest 30-year period that we have. The next one will be 1991, 2020. So in a year's time, in January, there will be lots of news about how the latest 30-year period looks like when you compare it to the earlier ones. In the old times, like in the 30s and 60s of the last century, the 30-year periods were like there was one and then you waited for 30 years and then you had another one. But today, because we have digital everything, it's possible to actually move the 30-year climate period. If you want, you can move it year by year. But what we typically do today is that we move it 10 years at a time. But the next one, the 1991-2020, is one of these official 30-year periods. The previous one was 1961-1990. Okay, so that is now the average here, which is a zero line, and anything above that zero line is warmer than the 30-year average, and anything below is cooler. So we can see here that yes, lately, most of the years have been warmer than the average. But still, we are only looking at like our lifetime period. What if we increase it a little bit and also increase the spatial scale? Now we are talking about Finland temperatures. If we go back to mid or 1850s, then the average temperature for Finland was approximately 0.5 degrees. And today, the average temperature for Finland, if you include Lapland and everything, is about 3 degrees. So the best sort of estimate for an increase for this period is about 2.3 degrees. As we can see, the different years vary a lot, so there is annual variability, but if you take a moving average, then we get a sort of smoother curve here. Okay, let's go to global scale and global temperatures, and now we have the time frame from 1880s all the way to the this is 2018, the last full year here. And again, we can see the trend of warming years here, and the variability is probably smaller than what we saw for Turku. Because of the big size of the Earth, it's moving slowly. It doesn't react as quickly as temperature in Turku, for example, which varies a lot, or in Finland. But anyway, we can see clearly this warming trend. And this, again, is also relative to a longer-term average. Here it's 100 years, actually, average. Okay. And currently, we are approximately 1 degree above the sort of pre-industrial temperatures. So the Earth has warmed about 1 degree. If we look at it as a spatial map, how the temperatures have changed, so we can clearly see that there are differences. Some of the areas, these sort of violet colors, have warmed more than the average. And we even find a small area in the North Atlantic where the temperatures are actually cooler than before. And there are good explanations for this. We can't go into those details. We can discuss it later, but it's to do with the North Atlantic deep water formation and Gulf Stream dynamism and so forth. And as you can see here, when we talk about a 100-year plus long time period, we are actually losing much of Earth's surface because there haven't been enough observations for this 100-year period. So we don't know exactly how the temperatures have changed in the middle of Africa or in the polar regions or on the Pacific Ocean, for example, because there haven't been thermometers around for that long time. Now we have those, but not 100 years ago, so we can't really tell. Years are different indeed. This is year 2017, and now we compare the temperatures with this 30-year period. And as we can see, in some places, like in Western Australia, for example, or Antarctica, that particular year was actually cooler than the 30-year period. Whereas large areas close to the North Pole have been warmer in that particular year. So it depends on who you ask. If you ask a person in Western Australia, in Perth, how is the climate changing, and if he only remembers, like typically we do, the last year or the year before, he says, no, it's been cold and probably the climate is not warming. But we really have to look at longer records and think sort of appropriate spatial scales when we discuss about climate change. Okay, but let's go even longer. What about 1,000 years? Now the problem arises that our instruments, our thermometers, have only been around not very long time. In Finland, the first weather station was opened in Kaisaniemi in Helsinki in 1829. So it will soon be 200 years old. So it's a long time period, but that hasn't been the case in all over the world. So when we go to the previous centuries, we don't have instrumental records. What we can do for these temperatures here, we can, for example, analyze tree rings, puulustot, or ice core records, or peat box for pollen, siitepöly, and so forth. And those are what we call proxy data. They give an estimate of the temperature at that time, but there is a lot of sort of estimation whether it's correct or not. And I could show you some slightly different curves here also. There is some debate whether these curves are correct or not. But anyway, it's possible to look at the temperatures for longer time periods. We can still make it longer. This is now 100,000 years temperature record. And this has now been actually, what we have here, the 100,000 year record, is one glacial cycle. I will talk about those a little bit later. And basically the period that we are interested in is about 10,000 years here, what we call the Holocene period. So that was the end of what we call the Ice Age, when ice melted from northern Fennoscandia and people could actually move to these regions gradually. And as we can see, the climate has been very stable for the last 10,000 years. And it wasn't the case during the Ice Age, so to say. There has been lots of variation here. And some scientists have now been connecting various sort of events in human history to these climate events and been thinking whether this has had an impact on what has happened. We can discuss that later. Okay, so this is 100,000 years. Let's go even further. Now we are more than 600,000 years record. And this has been cored from Antarctica. There was a European project called EPICA, where they drilled a hole through the whole ice mass of the Antarctica and they got like 3,720 meters deep, and then the drill hit the bedrock. And that happened 1 kilometer below the sea level. So if we removed the Antarctic ice sheet, there would be 1 kilometer depth of water in that place. Anyway, you can analyze then the ice core for various chemical compounds, because what is the Antarctic ice sheet made of? It's ice, yes, but it's actually snow originally. It is snow that has been precipitating on top of the ice, and year after year after year there is more snow, and gradually the pressure makes the snowpack solid ice. And anything that you have in the atmosphere at the time when the snowflake came down leaves its chemical mark on this particular snowflake. And you can actually identify the chemistry of the atmosphere inside the ice sheet. And this gives us an idea of the past climate. And what we see here is that now the present day is here on the left. On the earlier ones it was the other way around, unfortunately, but this is, here we have the present day, and these events here are the interglacial, the warm periods, similar to what we live now today, the Holocene period. And as we can see, it's interesting that these are rather short living. They are not long. Much longer are these cold periods here, the ice ages. And as far as we can tell, there have been about 20 of these ice ages altogether during the Quaternary period, which is about 2.5 million years in history. So it's not a single ice age, but there have been 20 glaciations and then warmer interglacials. And there is carbon dioxide concentration, then there is deuterium, which is heavy vety, hydrogen, thank you, and then methane. And all these can be detected, and they can be used as a proxy for temperature. And one more thing, we can look at this picture. The carbon dioxide concentration has been around 280 or 300 all the way during these warm periods in the past. And the lowest numbers that we find are 180. So there has been 100 unit difference in carbon dioxide concentration. This is one of the greenhouse gases in the old times. 180, 280. But it has always stayed there. And we will soon see what today's number is. Okay, so we can see that climate varies. It has been changing for a long time. We could go even longer time periods, but let's not do it today. But what causes these changes? We don't know exactly, but we have some ideas. Variations in solar activity. This is actually a parameter that some scientists believe is very fundamental and important. Earth's movements. We will go to these in a little bit more detail soon. I will show you some slides. So how the Earth is moving around the sun, and what is Earth's position, like the south and north poles, how they are positioned. Endogenic processes, meaning internal processes of the Earth, like volcanism, Earth's magnetic field, or lithospheric plate movements, mannerlaattojen liike. Those have an impact. Then we understand that climate is very complex. It's not only about the atmosphere, but we have to understand the interactions between different spheres, sfäärit, like atmosphere, hydrosphere, biosphere, lithosphere, you name it. All these work in interaction and can cause like cascading effects if it happens. One example is, for example, the ENSO phenomenon on the Pacific Ocean, the El Niño, La Niña cyclicity. And recently, human activities, so we believe, are one cause of climate change, and specifically the greenhouse gas emissions, but also land use and land cover changes like deforestation, urbanization, and so forth. And I will explain also this in a little bit more details. Well, let's go through these items that we just looked at. Sunspot activity. Here is a record of sunspot activity during the Holocene. So basically when there is a lot of sunspots, and a lot means a few tens of them visible on the surface of the sun is more active, and it's actually hotter than when there are no sunspots, or very few. And we can see that during this Holocene period, the interglacial that we live now, there has been a lot of sunspots like 9,000 years ago, and then the number has decreased, there has been lots of variation, and now there is some sort of maximum here. So could that be the reason for our climate warming? We know that we had a cold period, so-called little ice age here. We could see it on that graph before. And one of the best candidates for explaining this little ice age is the sunspot minimum during that time. So that sun's activity, so we believe, has an impact on climate. But how much? If we look at the latest records for sunspot activity, this is the temperature curve that we have seen before from 1880s to today's time, and this is the sunspot activity. And okay, here you could tell that perhaps they kind of correlate, although not perfectly in time, like the temperature has risen before this activity has increased, so it cannot really tell that. But since then, the sunspot activity has decreased, whereas the temperature rises. So it's not a good candidate for explaining what we see today. But what about the orbital factors, how the Earth, the planet, operates around the sun? There are three major parameters called precession, obliquity, and eccentricity. And briefly, they mean that this precession tells where does the imaginary line that comes out of the planet, the axis of our planet, the rotating axis, where does it point to? Where does it point to today? To North Star. That's the star in the sky that is stagnant. All other stars are moving around it if we take a long exposure photograph of a night sky. So it points to the North Star. But if we wait some 1,000 years, that has moved to another direction. So it's not good for seafarers after 5,000 years. They can't really find their north by looking at North Star. They have to find something else. So there is a sort of approximately 20,000 year cyclicity in where that points. And that has an impact on our climate. Then obliquity is the tilt of our axis. And that varies a few degrees back and forth. Now it's about 23.5 degrees. But it can be, so Earth can be more vertical or it can be slightly more sort of horizontal. It goes like this. So the axis moves like that, the precession, and then the obliquity means how much tilted the axis is. And the third parameter is eccentricity. And that tells about the orbit of the Earth, how it rotates around the sun, whether it's more circular or slightly more elongated. And that has about 100,000 year cyclicity. This is about 40,000 year. And if you combine these three, you get this yellow hassle here. And this is solar forcing at 65 degrees north, summertime. So it happens to be in Finland, isn't it? Finland is between 60 and 70 degrees north. And climate scientists, we think that it is the solar forcing, the solar energy, at this very latitude that can be a kind of igniting parameter for ice sheet formation in Fennoscandia in North America, where you have enough precipitation in the form of snow in order to create these ice sheets. So this is kind of crucial. But if we now see the stages of glaciation, the curve that we looked before from the EPICA ice core data, we can tell that, okay, there has been a warm period and there has been some sort of maximum here in this solar forcing. But it doesn't fit perfectly. So it probably tells us something about this cyclicity in the climate, but not everything. So there has to be something else. Maybe there is the solar forcing in addition. Maybe the sunspots are doing something. So we can't fully, or we cannot be fully convinced that this is the explanation. Milutin Milankovic was the Serbian scientist who invented or discovered this idea, and then, therefore it's called Milankovic cyclicity, this particular case. Then the last one of these potential parameters, I show you a diagram where we have ENSO activity here, the El Niño La Niña activity, and then some volcanic events. These ones are volcanoes erupting, and this is our temperature curve again. And perhaps we can tell that when there is a large eruption, these are the largest ones, there has been a short minimum temperature after these, perhaps. So we believe that a major eruption, volcanic eruption, may have an impact on the temperatures globally for maybe 2 or 3 years after the eruption, but not longer than that. Whereas the El Niño La Niña cyclicity, we can't go into that in detail, but basically these orange spots mean that the sea surface temperature in the Pacific Ocean, which is about 1/3 of the face of the Earth, has been warmer than average. That's the El Niño situation. And these blue periods are the opposite, what we call La Niña, when the sea surface temperature on the Pacific Ocean is cooler than the average. And this is to do with trade wind oscillations and so forth. But anyway, we can, if we start looking carefully, we can tell that whenever there is warm water on the Pacific Ocean, the global temperatures go up. And this happened, for example, in 2016, which is the warmest year on record so far. Since then, 17 and 18 haven't been as warm as was year 16, and that was because of the El Niño. Now we have had La Niña years with cool waters, but the next El Niño will probably give us a new world record again. When exactly, we don't know, but in a few years' time, for sure. But then we come to the anthropogenic issue. In 2017, this was the amount of carbon dioxide equivalent that we emitted to the atmosphere. So whatever unit you want to call it, kilograms or megatons or gigatons, you just drop some of the zeros away. So quite often we talk about gigatons or megatons here. As we know, the largest emitters are China, almost 10,000, USA, half of that, approximately today. Then comes India, Russia, and Japan. And now we can compare Finnish or Swedish numbers to these to get an idea. So the drop in an ocean is okay to say in this respect. And what is interesting, of course, is that although Sweden has a larger population, they have smaller emissions. They are doing something better than us, although not ice hockey. But if you look at the emissions per capita, so each one of us, then the map is quite different. You can't really make any red dots here that much. Finland So it's 10,000 kilos approximately, each one of us. So how many kilos do we have in this room? We could calculate that. Sweden 8, India 1.8. So we shouldn't blame Indians or even Chinese that you are doing bad, because they are actually, their emissions per capita are smaller than ours. And they are still producing much of our goods. So the emissions of our whatever garment go to the Chinese. The cumulative CO2 emissions of Finland are marked on here. From our independence, so cumulative year after year after year, we have now risen to 3 billion tons of carbon dioxide emitted by Finland. China emits this amount in 4 months. So that gives a perspective of, again, a drop in an ocean kind of thing. And this is quite interesting graph. Depending on how old you are, we can tell here how many % of the global emissions you have seen in your lifetime. So if you are 65 years old, you have seen like 90% of the carbon dioxide in the atmosphere has been emitted during your lifetime. Only 10% has been emitted before you were born. And even if you are 15, you have seen 30% of all those carbon dioxide emitted in the atmosphere. So that's kind of eye-opening. So what happens in the atmosphere then? There is an observatory in Hawaii on Mauna Loa. A chemist called Keeling established it in 1957, and it has been measuring carbon dioxide since then. And you can actually get, like this is the latest reading from the day before yesterday. That's the number, 410. And now remember, it was 280 was the typical maximum during these earlier warm periods. So we are now like 130 units above anything that we have seen during the last probably 2 million years. So this is 1 year record here. And quite interestingly, it goes up and down. Let's see what happens here. This is a 2-year record. So when do we have the maximum? Somewhere in May. And May. Then it goes down until September, and then it goes up again. What is this? This is now to do with biosphere. And the fact that on our planet, the lithospheric plates, the mannerlaatat, they are not equally kind of present on the Earth, but they are mostly on the northern hemisphere. And southern hemisphere is much ocean and just, well, Australia is there and something else. But it's the forests of the northern hemisphere continents that breathe and cause this fluctuation in the carbon dioxide content in the atmosphere. So during summertime, the photosynthesis takes carbon dioxide away from the atmosphere, and during wintertime, the breathing by all sorts of composting microorganisms, they breathe carbon dioxide back to the atmosphere, and this causes this kind of seesaw event, which we can clearly see in this whole record. But this is how the change has been since the opening of this observatory, from about 315 now to soon 415. So 100 units during this period. If we look at the bigger record from the sort of pre-industrial era, and this record is now ice core data. And this is the Mauna Loa observatory data. So we can see that there has been a huge increase during the latest decades. And this is how much carbon dioxide is in the atmosphere. This tells it. And carbon dioxide is the most important parameter in what we call radiative forcing. So when we get energy, which is basically light from the sun, there is a certain amount of watts per square meter that enters the Earth. And that is the radiative forcing. Or not exactly, because the radiative forcing actually tells us about how much of the solar energy sort of stays in our Earth system and heats the planet, because some of the solar energy actually is reflected back to the space without sort of interfering with the temperature, as I will soon show you. So carbon dioxide is the most important single component. Then there is methane, halocarbons, and then this, in Finnish, ilokaasu, or typpioksiduuli. What is that in English, by the way? Do we have chemists?
Dinitrogen oxide.
Dinitrogen oxide. Yeah, it must be that. Yeah. Good. Cheers. And all these are kind of positive in the radiative forcing. And these are long-living compounds. They can stay in the atmosphere for decades, centuries, even millennia. And then we have some short-living compounds, and they are not. Can someone press? What should we just press enter or something? Or just the cross? Maybe. Yeah. Okay. Thanks. Yeah, it tries to connect to the Wi-Fi, I suppose, something like that, if you click that. Okay, thank you so much. If you calculate or put together all these radiative forcings, the value is 2.3 watts per square meter. 2.3. Let's try and remember this number for a short while. And this is relative to the pre-industrial era, the 1750. And we can see how the radiative forcing has increased from 1950s, 1980s to 2011, which is the latest figure in the IPCC reports. The new IPCC report will be issued in 2021, and then we will get a new number for this.
Can you say IPCC report? Explain
yes.
1 second. What it is.
Good point. Thank you, Sabrina. IPCC stands for Intergovernmental Panel for Climate Change. And it publishes reports every maybe 6 years in these days, what are called assessment reports. And they are 3 thick books like this, like telephone books in the old times. And what we have seen lately, for example, a year ago there was this 1.5 degree report, which got lots of publicity. But that was not the real assessment report. It was a sort of, how do they call those? Special report. But every 6 years there is this major report. And we are now currently making it. Actually, I have it on part of it on my laptop. I have to give some comments on that. So it circulates among scientists, and we can comment what's in there. But anyway, yes. So the energy flows, we won't go in any detail in this, but what we need to understand perhaps is that what we get from the sun is 342 units. And now the radiative forcing change in the previous slide was 2.3. So that much those radiative forcing agents by or us, the humans, has now increased this number. And what happens here is that approximately 1/3 is reflected back to the space in the form of light, like a mirror reflects light away. And 2/3 are moving around here, circulating between the surface, which is heated, and the clouds, and the water vapor, and also the greenhouse gases here. They kind of stop the long wavelength radiation that we also emit to our neighbors now. We can tell that it's pretty hot here. So similarly, the Earth is emitting this heat to the space. But some of it starts to circulate here and it cannot escape. And this is what we mean about greenhouse effect, and this is what heats the planet. But eventually, basically, the same amount of energy that has to go back to the space that we get from the sun. Then we would be in a balance. But today, this number is a little bit smaller because of the greenhouse gases, and thereby the planet is heating up. What happens then when it heats up is that it is emitting stronger, like when you turn on your oven plate, and if you put it on 6, then it heats a lot, and if you put it on 1, then it's cooler. So the same happens with the Earth. So there will be eventually another balance if we are not continuously emitting more carbon dioxide. Okay, how about the future then? Future of the planet. So the climate system looks like this, and what is important here is that it's much more than just the atmosphere. Although many things happen here, we have to understand that there is atmosphere, hydrosphere, cryosphere, land surface, biosphere, and human influences here. And all this we have to put together when we make our, now I have a wrong slide, the story line kind of cut, but sorry. Yes, we have to understand all this, and when we make our climate models, we have to try and model all these components and get parameterization for these. But the slide that comes here, I see, is an indication of how various things are connected in our Earth system. So we say that the climate is kind of systemic in nature. So if something is happening in the Greenland ice sheet, say it melts like it melts today, it has an impact on the Arctic summer sea ice. I will show you an example soon, if I have time. And it may have an impact also to the Antarctica, to the Amazon rainforest. So all of these are connected in various ways. And we should understand what happens in these particular cases. And if something happens here, we have to understand that it may have an impact somewhere else. And that makes it so difficult. So this is the slide that I was expecting to see. So the climate models, this is a very simple sort of intermediate complexity model, so-called CLIMER. This is an old one, almost 20 years old, but I like the image. It explains us quite well what is going on. So we have the sun here, we have the atmosphere, we have the inland ice, so the big ice sheets, we have terrestrial vegetation, and we have the ocean. And then we put all of these together in this sort of center piece where all of these components are kind of coupling and influencing each other. And then, of course, we have our Mustapekka, the human beings here. We are emitting aerosols, greenhouse gases. We are changing the biosphere, deforestation and so forth, and thereby influencing the whole system. So the climate model tries to quantitatively analyze all this, and obviously it's quite a tricky question. The models have improved substantially. The first IPCC assessment report was published in 1990, and at the time we had climate models that sort of were able to have CO2 there, and the rain was there, some land surface, maybe some clouds, but nothing else. And the spatial resolution, this is the Europe, looked like that. So it was not very accurate in that sense. But gradually, as the computers have improved and the computing power has increased, we now have already since 10 years ago in the fourth assessment report, we had Europe as it looks like in real terms, and we also had all sorts of components in this model. In the first models, there wasn't any ocean, for example, which was a serious default. Then the ocean was 50 meters deep, swamp ocean, and eventually we got the proper ocean there and so forth. Okay, so what do these models then tell us? Now we come to another quite well, difficult, not difficult, but I have to explain it a bit. We have now emission scenarios. Basically, when we try to figure out what will happen with the climate in the future, we have two sort of crucial things. We have to have our climate models, the physical models that actually do the computing. And then we have to have an idea, a guess, a best guess of the emissions in the future. And those we don't know. I mean, we know probably the emissions for the next year and the year after, but maybe after that something happens. Someone creates something, an invention, hydrogen power or something like that. And suddenly the emissions change rapidly. So we don't know what will happen, but we have to guess these emissions. And they are called now representative concentration pathways, or RCP in short. And we have different RCPs. And this number here, 8.5, 6, 4.5, 2.6, refers to the radiative forcing that we had in an earlier slide. And if you remember still the number 2.3, now the lowest scenario that we have for the future is that the radiative forcing would only be 2.6. And probably that is a dream, because I think we have already exceeded that 2.6 today. The next one is 4.5 watts per square meter radiative forcing, then 6 and 8.5. And depending on what we then eventually have, there will be certain temperature. So this figure gives us the temperature of the Earth as compared to the pre-industrial time in 2100 with different scenarios. If we go with the RCP 2.6, the Earth will be approximately 2 degrees warmer than in pre-industrial time. So we would get another 1 degree warming after today. That wouldn't be too bad. But if we have the RCP 4.5, which means that there are more emissions, the cumulative emissions are shown here. Then we have like 2.5 degree warmer. And the worst case scenario, the 8.5, means that we have emitted almost 8,000 gigatons of CO2 by 2100, and the Earth would be 4.7 degrees warmer, approximately. This kind of fan here, this brownish or reddish, tells us the difference between different climate models. So depending on what model you use, you get slightly different warming numbers. And there are about 20 models at the moment by different scientists in different countries that we use. And we don't know which one is better or worse. So that's why we show all these here. But that's how it goes. So depending on our emissions, by the end of this century, there will be a dramatic difference in temperatures. But not necessarily yet in, say, 2050. In 20, 30 years' time, we can't really see much difference between these. We are warmer than this one, but still, I mean, these do not deviate much, but only after that. And many of us will not see that, me included. So it really is our children and grandchildren that we are now talking about here. And again, we can look at this warming as how they would look like as a map. So the warming would be greatest in the northern sort of circumpolar region, where we can end up having something like 5, 7, even 9 degrees warmer. And if that happens in Finland, it means that the current sort of winter climate of Turku, which is about -5 degrees, we find that in Lapland. And anything south of Lapland would be similar to what we now have in the Baltic countries or Poland or somewhere else. So we have to say goodbye to our snow cover in rather short time in Turku, as we have already seen that it's becoming sort of unstable. Okay, I'm coming to an end now, and my message here is that although we are interested in climate and concerned about climate, climate is only a symptom of our unsustainable way of life. And personally, I think that we have to change our habits, not only because of climate, but because of all other things happening in the world. We are causing crises everywhere. But if we do that, then we can simultaneously improve the climatic situation. This is an example of what is happening today in the world. There is somewhere perhaps carbon dioxide. We have seen this figure here in earlier slides, but whatever, paper production, water use, anything you look at, it's going like up and up and up. Tourism, transportation, so forth. So we should somehow get something different, because there is an idea of sort of planetary boundaries, a term planetary boundaries, and it means that there might be a boundary somewhere or a threshold that we shouldn't exceed. If we do that, we don't know what happens after that. And this example is very simple. It's about the carbon dioxide concentration, parts per million, the units that we have been using so far. And then the response variable here is the extent of land ice, for example, the ice sheets. And they may actually collapse at some stage if we just heat the planet. They will not gradually melt away, but there is actually a dramatic, like a threshold. And if that happens, then the ocean water levels will rise in probably decades or centuries. Again, long time periods for us humans, not our problem, but yeah. And this is probably why it's so difficult for us to understand this. Here is an example of the Arctic sea ice. So the ice that is forming every winter around the North Pole, and then it melts during summer, like the ice in the Baltic Sea. But the difference is that this ice never melts away during summer, because it melts and it decreases until mid-September, and then it starts to grow again. And these are millions of square kilometers here. So it goes down to approximately 7 million square kilometers by mid-September, then it grows back to something like 15 million. But now, 2012, we had the smallest ever measured extent of the sea ice. And this is this year's line, the blue one here. So we are now going quite similar to what we have seen earlier. And this is again the 1981 to 2010 average or median extent. So it's continuously shrinking. And if you remember the earlier slide where I showed the connections between these different items, if we lose this ice cover during summer, it means that it doesn't reflect the sunlight away, but it actually absorbs the energy, because the sun is continuously above the horizon during summer there. And we will start heating this area, and it will increase evaporation, and it will increase precipitation, and then we don't know exactly what happens after that. So it's a cascade of things. So what's the remedy? I have listed this like 13 years ago already, and I have been thinking, when can I drop this slide that I don't have to show it again? And soon that may happen, maybe after this evening, because I think that this not true thing, that there are not that many denialists around. Maybe there are some in this room, hopefully, and we can discuss later. Then quite often we argue that it's not my business. It happens somewhere else, somewhere in Africa, doesn't matter. But after 2015, as we know what happened, suddenly we realize that, okay, things may happen on the other side of the world, and suddenly something is knocking on our door, and it is our problem also. Then we have the land of commons problem. The fact that, okay, China does that and we don't, why should we do something? But I think we also have opened our eyes regarding that it's actually individuals who matter and not the countries only. Then quite often we say that it's too expensive to do something, but again, that has been also sort of dropped because we know now for sure that it will be much, much more expensive to make changes after, say, 10 years or 20 years. It would be cheaper now if we just make the investments. But the last bullet point is still there. Even if we say yes to all of these, that I agree, but what should we do? We know exactly where we should get, but we have no idea how to get there. I think that's the tragedy here. We had the Paris Agreement. It has been approved almost everyone, not USA though, and nothing changes. There is no sign in our emissions or anything, although it's several years after that. And we have these planetary boundaries, and climate change, as you can see, is not in a sort of critical status at the moment. So the further away from the center you go, the more dangerous we get. And actually the biodiversity has already entered the sort of red zone, that we have the 6th extinction wave now going on the planet. And another one that is on the red zone is the biogeochemical cycles or flows regarding nitrogen and phosphorus specifically. And this is to do with our farming and fertilizer use. And then we have other things here which are not as in a bad shape. So we have to consider these, the sort of ecological boundaries. But then we have another challenge. If we consider these, take care of these ecological things that are now here, we also have our social issues that we have to consider, like food, health, education, peace, political voice, and so and so. And how do we, this is called the donut economy, meaning that humankind should find itself in this green zone so that we are not exceeding or overshooting the ecological boundaries, and we are not shortfalling of the social foundation, so that the poverty and other social constraints would be away. And if you consider Finland, then we are doing quite well with these social foundations. We have some unemployment, yes, but that's more or less the big issue. But Finland is overshooting almost all of these others. So many people argue that the sustainable development goals could be the solution here. Why not? I'm sure you are all familiar with these, are you not? There are 17 of them, and they are now sort of operative for 15 years until 2030, and then there will be something else. Who knows what that is? And as we can see, there are good ideas here, and behind all of these there are sort of sub-targets. There are 169 sort of smaller targets behind these, and this is what most societies today actually are trying to sort of follow these ideas. But the problem here is that, oops, I have the Finland example here, how we are doing regarding the SDGs. We are globally ranked 3rd, so we are 3rd best in our sustainable development goals of 162 countries that are there. And guess who are in front of us? There's Sweden, of course, and Denmark. And I think Norway is then just behind us and so forth. But even us, we are not doing that well in all of these. And funny thing, for example, is that this is SDG number 2 is zero hunger. It's the title, so flashy title. And if you look at SDG 2 here and Finland, we are not doing well at all, because if we are reaching this 100, then we are doing good. So for the no poverty, we are there at 100, but no hunger. What's this? It actually means that we are eating too much. So the no hunger is just a flashy title, but what it means is that we have healthy nutrition. And Finland has the opposite problem. We are not suffering from hunger, but we are suffering from eating too much. That's why we are not doing that well here. So these are actually very tricky things to put together, and there are sort of synergy pairs where things seem to happen in the same countries. Like these, you can see that these are like okay things. There is quality education and there is reduced inequalities. They happen in the same country. But then there are lots of examples of trade-off pairs where things do not coincide or they work to different directions. And as you can see, it's almost always the SDG number 12 that is the problem. And it says responsible consumption and production. So we are basically just producing too much and consuming too much. And that basically compromises all the other SDGs, if you think of the global situation. So we should reduce. But how can we reduce? Because we want eternal economic growth. So we still haven't found an answer, I'm afraid. I stop here. Thank you.
Thank you so much. It was an amazing, fantastic talk. I really, really want to thank you. And I'm so happy that this is our 50th anniversary with this talk, because it's really an example of the reason why we are doing this Science Cafe. So thank you very, very much. So questions? Yes.
Don't you think in the slide, in the dark blue slide where you had listed 5 different attitudes, don't you think you should add a sixth attitude, namely the attitude that you agree there is climate change going on and agree about all the other things, but you don't care? Because I think in everyday conversation with people, you meet people who know and agree, but they don't care.
Yeah, that's a good point. Yeah, you are right. It's not exactly any of these. Even if you say that it's not my problem, even if you say that, okay, it's my problem, but still I don't care. That happens. Thank you.
But might it be because they are not, they don't know enough? Might it be because there may be different, I think that what you're trying to do here is to identify reasons why people may not care. I mean, of course, people generally may not care, but there could be reasons, and the reasons could be different, and maybe one way of sort of trying to, make people change their mind about the I don't care is to understand better what is the reason why they don't care and try to act on it. I don't know, I'm just saying.
Yeah, well,
but yeah, sorry.
Let's consider this. Okay, go ahead.
I want to answer you. I think it is people are fundamentally different. That's a problem or issue of people have different characters. Some people just don't care, no matter how much they know. But I hope you are right and I'm wrong.
I don't know who is right and who is wrong, and of course I know that there are differences, but of course you have to, I guess you have to work on the average in a way. There will always be people who will just not somehow be willing to, for a reason or another that we don't know, but it's sort of one tries to, I guess, I don't know, I don't have answers as well.
Yes, but it would be, I think that you are right, that there are people who don't care regardless of how much they know. And it would be interesting to try and figure out how could we make them care? Because obviously it's our common challenge, and we should get everyone to care about this, I think.
I have
Yes.
a follow-up question about people. Yeah, so I come from Russia, and well, during Soviet Union times, despite all the bad things that were happening, actually, like recycling and tree planting and whatever was quite on the rise. And I'm also the industrial production was going on a lot. But I think now when I have conversations with my grandma, she always says that, well, we've done all of that and it didn't change anything. And the Soviet Union was taking quite a big part of the territory still. So it's kind of, I don't know if it's a question or more of a, it's kind of, I think we have quite as you were saying, that climate is on a big scale, but we have also kind of a short scale social memory sometimes, and especially the younger people, they have seen a certain the period of like consumption practices that they have experienced, and then they try to go back. But for example, my grandma remembers, now we are all using glass containers, for example, and it's considered to be more ecological to do that. But my grandma remembers how they were going away from glass because glass was too difficult to recycle and plastic was easier to recycle. So everybody was actually more concerned that people start using plastic products. So, yeah.
The question is maybe about consistency.
Consistency and how to keep kind of social memory of.
Yeah, well, I understand, yes, thank you. Well, the consistency or inconsistency, I think is one of the problems globally, because it's easy for us in a welfare nation to do things and make decisions, but I also work in Africa, and those people are just trying to get out of the poverty, and the remedy for them is completely different from us. But how to do this? I mean, you are right, we have different individuals who either care or don't care, then we have different countries, then we have different age groups. Some people have longer history, longer understanding. They remember things that were better or worse, who knows? And it's such a combination of different expectations. And I mean, my interest now is that my children do something, for example, and someone else is interested in whether he gets a job or simple everyday things. And simultaneously you should think about global challenges, and how to do that is, so far it has been impossible to solve. But yes, about the knowledge, or how much we know, you know probably how much water is used to produce 1 pint of beer, approximately. It's 75 liters. Does it stop us drinking beer? No. Should it stop us drinking beer? I mean, we have plenty of water in Finland, so it's not a problem. But is it a problem globally? Maybe not. And about eating beef, all these, I mean, we have so many things that we should think about continuously when we go and do shopping. What can I buy? Can I buy a bottle of beer, or is it am I a bad person, and so forth. It makes life impossible to live, or at least enjoy, if that happens. So the information and understanding, they are different things. That's why I had that last slide.
Yes. Yes.
Can I ask 2 clarification questions? So the one is that there was the slide with the sunspots, and it went all the way back to far in history. So my question is, who looked at those? How can you know sunspots in the past?
That's a good question, isn't
that
it?
was my first question. And the other one was about the El Nino and the air.
Mm-hmm.
That somehow kind of temperature is an interaction. So how is it kind of known whether it's the water kind of affecting the air temperature, or whether the air temperature is kind of affecting that the water cannot get rid of the temperature?
Okay, thanks. The first question here is, it's actually said here in the small print. So basically we use, again, ice cores and tree rings, anything that gives us sort of annual or semi-annual information. And we have two isotopes which are sort of cosmogenic isotopes. There's the carbon-14 and beryllium-10, which are formed when based on this, or depending on the sun's activity. So the amount of these two compounds in our sort of layered sediments, whatever, tells us about the solar activity. So that gives us this information. There wasn't anyone at least making records of sunspots 5,000 years ago, even if they somehow could see them using some device. Because we can see them if you use those glasses that are made for looking at auringonpimennys, solar eclipse. Yes, solar eclipse. So very dark glasses. Then you can look at the sunspots as well. But yes, so it's basically chemistry. And this has an impact on if we are dating some old, whatever, bones or something using radiocarbon, we have to then correct it to the changes in solar activity in the past. So it's actually quite well-known system, this. And the next question about the this El Nino thing, I only have this. This is what you referred to. Well, we know the mechanism of this ENSO system. So we know that during some periods, the trade winds that blow from the northeast on the northern hemisphere and southeast from the southern hemisphere, so it's Koillis-Pasaati and Kaakkois-Pasaati, the trade winds, kauppatuulet, because the sailing ships use those. They normally travel from east to west along or near the equator, where you have the trade winds, and then they return closer to the pole at around the western winds zone. If anyone saw, was it yesterday's Turun Sanomat about this scout boat, Tokkalotta, there was a full page article about scouts, partiolaiset, sailing to the Caribbean Sea now. Did anyone notice in Turun Sanomat? You don't read newspapers? Good. Not Turun, yes, fair enough, yes. Okay, but their route was there marked, and they actually go like, they are now on Canary Islands where they start, and they really sail with the trade winds to the Caribbean, then they sail on the east coast of the USA, slightly norther, and then they return on the northern route. So we know exactly, or quite well, how this planetary wind system operates. And the wind that blows from the east, it pushes the surface water on the Pacific Ocean towards Indonesia. So if the winds blow hard, then all the warm water on the Pacific Ocean is pushed to the Indonesia, and there is cold water sort of coming to the surface from deep ocean near Peru coast on the South American side. And that then covers much of the eastern Pacific, and this is the La Nina situation, where there is plenty of cold water on the Pacific Ocean, and that cools down the Earth. And then the opposite happens when the winds, the trade winds, almost stop, that they don't blow, and this happens occasionally. and then the warm water covers the whole Pacific Ocean. So we know that there is a causal relationship so that the El Niño or the ENSO cyclicity affects global temperatures and not vice versa. Yeah.
Thank you. So more questions? Yes.
There was a slide where you had the reflection of the power of emitted by sun to the surface of Earth in meters. I remember that I had a course in university where we talk about this albedo.
Mm-hmm.
So our professor told that it's crucial to have a life. When we have a life in Earth, we have a crucial that this back radiation happens.
Mm-hmm.
So can we now do something that causes the back radiation to stop? So we have less radiation to Earth, or we just don't have clouds, or we color all the black asphalt to white so we have more reflection.
Yeah.
So can we do something drastically to reduce this greenhouse effect?
Yeah, good question, thank you. So indeed, 1/3 of the radiation that comes, this is the solar radiation coming in, 1/3 or 30% roughly is reflected either from the clouds or from the surface. Yeah, so this is the albedo, as it's called, the reflectance of the Earth. And the more white whatever there is on the Earth, the more it reflects. So if we have lots of clouds, they reflect. If we have snow or ice, that reflects. If we have dark surfaces like asphalt, or even boreal forest is dark, that then absorbs the energy. And indeed what happens here, that the energy starts to kind of circulate here. It's re-emitted back to the atmosphere. It cannot escape, but it goes sort of back and forth. And this is why there are such high numbers here, higher actually than the incoming values here, because they bounce back and forth. Eventually they then get through here. And now indeed people have been discussing whether we should somehow increase this or then decrease this system here. It might help, but I don't believe it, honestly, that if we start painting things white, that would have an impact, because it's still a tiny portion. What we shouldn't allow happening, for example, is the decrease of the summer sea ice on the Arctic Ocean, but it's now happening and there's not much we can do about it. So the white areas are kind of disappearing from the Earth. We know from the long history of the Earth that there probably has been a time period, like hundreds of millions of years ago, when the whole planet was covered with snow and ice. So it was a so-called ice ball Earth. There are some evidence of that, but it's debatable whether it happened or not. But most scientists, I think, believe that it happened. And it only stopped when there was so much volcanic activity that it broke the ice cover from the oceans, and it emitted lots of dust and also carbon dioxide on the atmosphere, so that it gradually then melted. Because the sun was much weaker in the early times. It's about 30% stronger than it was when the Earth was young. So the solar activity is continuously growing, and the funny thing here is that even though it's getting stronger all the time, we now have had 2.5 million years of ice ages, which tells us that there is some sort of thermostat operating in the Earth. It's not only the solar activity, but it's somehow very fine-tuned system that we have here. And now we are afraid that maybe our activities have somehow broken that thermostat. And we know what happens if we break a thermostat on our batteries or radiators. We are quite unhappy typically. Either they are too hot or cold. But yes, your question about what could be done, there are these geoengineering ideas of spreading some reflecting something in the space, for example, but that is highly dangerous. We don't have any idea what that happen after that. And how do we remove that if if we find that it was a bad decision. It should be something that we can actually reverse back. And if we take something to the space, it's probably quite difficult to take it down there. Sahara, for example, has not always been a desert. 6,000 years ago, it was a savanna.
Okay.
And that was, how does that affect albedo? It's actually darker surface. So it was a heating element at that time, and now it's good that we have Sahara because it's reflecting the sun away. So, and now someone wants to plant trees there. So it's kind of debatable. Maybe you get some of the carbon dioxide away, but you would also decrease albedo. And ST1 person who is behind this idea probably doesn't know.
Yeah, I have one question about the carbon sink, which has been discussed lately in Finland quite a lot, and it seems that the calculation varies 100% here or there. What is that exactly?
It tells us that we don't know exactly what is happening. It's quite easy to calculate the amount of carbon in the trees themselves. That's quite straightforward, but there is more carbon stored in the soil of a forest than we have on the trees themselves. And this is where the differences come out. And also the fact how we then treat or manage the forest, whether we make a clear cut, avohakku, or not, will have an impact on the carbon in the soil, whether it's released or whether it stays there. And quite often what we don't remember or don't recognize in our everyday speech is the difference between carbon storage and carbon sink. So carbon storage is varasto, so we are storing the carbon, and sink is the nielu, that we are actually increasing the storage. And sometimes I see that people are talking about different things. One is talking about storage and one is talking about sink. And we can't increase the sink or the storage like eternally. There is a maximum storage that we can think of. And if we think of the fossil fuels now, oil, where did oil come from? What is it? What it used to be?
Living cells. Life.
Plankton. It's actually plankton. And the coal used to be forests, or peat perhaps. And if you think of how much forest you can grow on this planet at one time, it cannot possibly hold the amount of carbon that we have now in the coal, because the coal has been formed over millions of years, and there are probably hundreds of forest generations being accumulated and packed very tightly. And there is so much more carbon in the coal than can be stored in our forest at one time that the equation doesn't hold. That's the problem. So I think it's kind of nonsense to talk about increasing the sinks. We should stop the emissions.
Okay.
Or decrease the emission. We can't stop them.
Sorry.
Thank you. Very interesting talk and topic. I would have two questions that are quite different, but well, maybe the more important is the when you showed the graph for temperatures and when the ice ages are here, and it seems that we are now in the hundreds of thousands of years we are in the upper temperatures, and because of the where sun is, how is the spot activity, where the Earth is circulating, and so on. So it seems that that is partly the reason why we have the hot times. But of course, naturally, the carbon dioxide is increasing and doubling even. So we do have effect. But when should we expect this hot season because of sun and Earth to stop? Should we expect this to turn down at some point?
That's a good question. Would we be happy? My question is, how would we react if we were now going towards a new ice age. Would that be a good situation? Probably
not. For Sicilian.
Probably not. So, as far as we understand, and I think I have to now move to this one. As I mentioned briefly, these have been very short, these warm seasons or warm periods. Sometimes longer, yes, especially here they have been longer, and now they have been very short. Whether this would be similar, so to answer your question, if this holds good and we don't really understand how it goes, we would be expecting to get back to a glacial period rather soon. And actually I remember my professor told me once that in the 70s people were actually concerned about the new ice age coming, because we didn't really see at that time yet the warming. And there was the little ice age, and then we had a warmer period around the Second World War time, and supposedly nothing to do with the war itself. And then there was a drop of temperatures in the 60s and 70s, and people were like, oh, now we are entering the new ice age. But that was a short period, because then we realized, or those people realized, that we are actually heating the planet. So supposedly, yes, we would go towards the ice age soon, like in 1,000 to 1,000, 3,000 years, something like that. Not our problem. It doesn't happen so fast. So possibly we can now stop the new ice age coming or delay it. And thereby you might argue that we are doing good.
Okay, more questions?
It's just a follow-up question to that. Would it be actually good that we stop that ice age coming? Like, aren't we messing with the Earth a little bit in that sense? That wouldn't it be natural for it to come?
Well, as we had this slide showing this one exactly, Holocene, the last 10,000 years have been very stable climatically. Nothing similar. Well, there has been quite stable, but not quite anyway. So, yes, we have been lucky. Or maybe it's not luck. Maybe all our cultural evolution is thanks to this stable climatic period. So what would be best for us is that that would continue. So perhaps we should be so careful in our geoengineering that we are not heating the planet too much, but we are stopping the coming ice age and try and keep it there. I wonder if we could do that, but that would be a nice... Why would we do that? Is that your question?
Yeah.
Well, I think most of us would be happiest if things continued as is.
To survive.
Rather than heating or cooling. I think the whole society has been built over decades to have certain types of houses and study tires during winter and this and that and that. So it's all very what's the word now? Optimized to current conditions, and any change to any direction is typically unsatisfactory, I suppose.
Like at the very least, probably will cause death. Like sudden drop in temperatures, sudden rise in temperatures. At the very least, will cause a lot of people to die, especially in developing countries.
That's true.
So that might be it.
But I think, I guess, maybe I'm interpreting your point of view. The point is, of course, this puts us at the center. I mean, our survival is the thing, the most important thing. I mean, we are seeing and assuming all of it from the perspective of us being important.
Who is us?
Or not in terms of,
the
cycle of, Earth and universe, whatever. I mean, it is everything optimized to the fact that we want to survive in the best possible way as society. I guess this is what you meant. While, of course, one could also take up points of view, okay, we can be, gone by and still things would continue, and, well, that's okay as well. I assume, I don't know, it was an interpretation.
Well, if we think of the history of the planet and the extinctions in the past, I think the most probable situation is that the human race will disappear and go extinct at some stage, and the planet continues. We have only been here for such a short time period now.
And
A
on
few
this happy
hundreds of
note-
thousands of years.
Sorry, next question.
Hi, thanks for the nice talk. I remember reading somewhere that like global warming is not a process in which basically every spot on Earth just warms up a little bit, but instead there will be like very extreme events like I guess we've seen recently, like heat waves. Could you comment a bit on that? What possible effects one might expect? Because this could happen even shortly.
Yes, exactly. That's a good point. I just didn't have time to go into these. I think I had this. Do I remember now? Are we going to the right direction or not? I'm looking for this map. Yes, it's coming. Probably next one, or the next one, or the next one. This one, yes. So clearly it's not even, whatever happens here. But these are, again, averages. And now you were talking about hazards. And that's totally another picture. So we would, if we think of, this is just temperature. But what is the most crucial change that we expect to happen? The sort of black and white, so an on-off change, is the rise of sea level. Because temperature can rise like 1 degree, 2 degrees, and it's sort of, yes, okay, it's more difficult. But suddenly if you have water or no water, that is like on-off situation. And we have so large populations now, hundreds of millions of people living at so low altitude, like below 1 or 2 meters above sea level now. Major cities, that when our sea level rises, then it's a serious problem for those societies, and that we are talking about hundreds of millions of people in probably by the year maybe 2100 or thereabouts. And when you then combine, for example, what seems to be the case, that the cyclonic activity, the hurricanes and typhoons, that their frequency is increasing and their momentum is increasing. And when you combine the rising sea levels with these sort of flooding events due to these storms, then that's serious. So temperature is not actually that interesting, although, yes, we do have these extreme temperatures that can kill. And then agriculture, what happens with that? Food production. But then we have biodiversity issues otherwise, like if we lose the pollinating insects, suddenly we don't have a food production. And whether that is to do with climate change or is it some other factor, as we know it is something else than climate change that affects biodiversity at the moment. So we are in the middle of problems, really.
Okay, let's see. Yes. Maybe there is one question. Yeah. First, because he has not asked yet. Yeah. Pointing. I thought you wanted the microphone.
No, I was pointing because I showed that please give him the mic so he can ask the question.
Thanks for the interest. I saw one TV program, something as scientists saying not only sun activity, but also our solar system circulating in Milky galaxies. So galaxy is not flat. Somehow the crowded area and not crowded area. So some point our solar system go into some crowded area, sometimes go out from the such kind of thing. So more big scales, some happen to the change everything. So what do you think such kind of more, not only about the sun activity?
Well, that is definitely something that we cannot help and shouldn't probably worry about. Of course, what will happen eventually with the Earth and our solar system, as we all know, is that the sun will eventually die. And before it dies, it expands. And as far as we understand, it expands so much that the orbit of the Earth will be actually inside the sun. When that happens in some billion years, then that's the end of our solar system and the Earth and our sun as well. So by then we should move to other planets or other solar systems actually, like some people already are keen on going. I'm not. I would rather try and keep this livable, this planet.
Let's hope that Mr. Elon Musk will save us.
Yes, he and
the
his
first step.
2 friends can go to this.
But my question would be, not a question, but because you mentioned the Sahara, and I remember reading some article where a German engineer somewhere beginning of 20th century made a suggestion that Sahara would be, that there would be digged a canal to Sahara, because Sahara, is it true that it's below sea level?
No. There are small areas.
Right.
There is in Western Egypt. There is actually an area which is some 120 meters below sea level, which is quite large.
Do you know this theory that?
Yes, I've heard of it.
And what do you think about that? If we would dig this and there would be a kind of a Sahara inside sea, which would then produce some clouds and such, and what do you think about that?
Yeah, well, I would probably try something more simple first, honestly.
Okay, I have a question related to this one that is almost like you just say almost like a private, personal question. That is, of course, you say that it's a very complex problem, and clearly this is also something which is, it doesn't have a unique solution, a unique answer. We don't even know the answer. Certainly needs to be diversified for different parts of the world and for different type of populations. We all know it. But I mean, I'm not asking you to give your recommendations of things that everyone can do in their daily life, but how about yourself? I mean, what are the things, because of course you as a human being and part of this society and knowing that this is something that is important, has this have an impact, or which little changes you did in your daily life for somehow trying to do something that is not at the level of these huge possible ideas, but something that everyone can contribute to.
Yeah, thank you for the question. Yes, I try to be good person in climate or climate-wise, but it's not very easy in our society. Although our society, as we see, Finland is doing very well, but it's like inbuilt system where consumption is part of our life. So I live in a detached house, omakotitalo. What if I moved to somewhere here and sold my omakotitalo? Someone else would live there, maybe not as conscious about climate as me, and suddenly the emissions from that building would increase. Would that help? So we are kind of locked with our societal structures, that even if we personally do something, if I sell my car, which is polluting thing, to someone who drives more with that car, what is the net effect then? So I used to have a Range Rover, old, like Jeep, and it was a terrible car in terms of fuel consumption, but I drove as little as possible, and I always said that if I keep this in my yard and not drive, then it's better than someone else driving a lot. But yes, what I have done is that I have changed my car to ethanol. So it uses bioethanol. It's basically made of waste. I buy only wind energy. I have a maalämpö thing, and I have a plug-in hybrid. I have a car, yes, but it's plug-in hybrid and indeed ethanol on top of that, so it's kind of as good as possible. And I don't eat meat apart from game, basically, because I think that, well, game. Because we have killed all the wolves, someone has to eat the deer and elks. Otherwise, they would be all over the place. So it's kind of a chain reaction to this, and so forth. So I do my best, but I think that my carbon footprint is still much, much too big.
Are there any places where, you know, like websites or things like that, that you would, you know, recommend, or that when one can have some suggestions about?
Yeah, well,
because the problem is that there is a lot of, it's so difficult nowadays to take decisions, because you hear everything and the opposite of everything, and there is a lot of course we try to give some information that is as close as possible to scientific facts, obviously for us is important, because, well, what else can we do? But of course, maybe there might be, that's why I asked about the recommendation, there might be some sites or some recommendations that people could go to, and of course, eventually it's a personal choice, but I don't know.
Well, how many has done the hiilijalanjälkilaskuri, the
oh
carbon
God.
footprint?
What is it? Some help, some person who translate.
Have you tried it? Carbon footprint calculator.
No, no, we haven't.
Have you done it?
No.
Who has? Not that many. Well, now when you go home, take that Citra. Citra has a carbon footprint calculator, and you can just, it's not easy to put the numbers in because some of the questions are not suitable for you. That's the problem. So it's kind of an estimate, but it gives you an sort of estimate of your own carbon footprint. And the average for a Finnish person is 10,300 kilos. I don't know how that has been calculated, but that's what they say. And yeah, it will be eye-opening perhaps to see your own, whether it's bigger than smaller than the average. And it also shows you where is your largest consumption. So then you may be able to make decisions. Okay, actually a large proportion of my consumption is because of me doing lots of shopping. And that is something you can decrease, for example. But if it's traveling, maybe you can stop that as well. Personally, of course, because I'm a scientist and I work here and there and I have to go to conferences and so forth, I fly too much. But actually I haven't flown now for 2 years more than once. So I haven't been to the conferences anymore. But that actually is kind of a problem for a scientist, as we all understand.
Yeah, well, it's very, thank you very much. That's very interesting and useful information and question.
There was the slide where you had to measure the length of the ice that was drilled in the Antarctic, and you had the second slide where you had this. It was in Hawaii, the station. So how do the last part of the ice correlates with the station measure? This, yeah. So how well does the concentration of these greenhouse gases correlates with this slope that we have measured in this station?
You mean this part?
Yeah.
Well, well, the question goes actually that not much of the snow that has precipitated during the last 50 years, or none of the snow has turned into ice yet. When the snowpack has to be actually tens of meters of thick before there is enough pressure to make it solid ice. And about 60 meters deep ice becomes then kind of soft and mobile. So when you have 60 meters deep ice, then at the bottom it's not solid anymore, but it's plastic. And then it can start flowing. As we see the glaciers on the Alps, for example, they are coming down the valley, and it's because they are so thick and in this high pressure the material is plastic. But none of this snow that has precipitated during this time is not yet ice, so it wouldn't make much sense to try and make it, but it should definitely show this same signal. But this is measured directly from the atmosphere, so it's kind of more accurate. This is from the ice cores, so that gives you an idea how bad resolution there is. You can't see actually the annual variation that well.
So we have to wait something around 300 years to wait that ice actually forms, and then we can make this kind of.
True. I don't know now. I don't remember the metadata from which ice cores, maybe from several ice cores this data has been derived. But there is somewhere an ice sheet or glacier where they have been able to take this sample. But Antarctica, there is so little precipitation. It's very dry. It's one of the driest places on the Earth. There is very little snowfall there. So also the ice formation is very slow. Greenland is much more humid and there is more precipitation and the ice gets thicker faster, but we can't get so far back in time. We only get back maybe 150,000 years in Greenland, something like that. Not longer than that.
Okay, we have maybe time for a last question. Let's see if someone wants to ask one more question. Well, there was a very, very nice debate, I think, and very many questions were answered.
I have a question.
Yes, that's nice, and it's a first. We like it.
Is anyone going to change his habits after this presentation?
Well, I just said yes, but I wasn't prepared to say how. Okay, let it go. Because I'm drinking beer without alcohol every day, about 1 liter beer. And you said it takes 75 liters to produce the beer. And that was a great surprise for me. So I'm afraid I have to reduce my beer drinking. Thank you.
Okay, but maybe reduce coffee drinking instead, because coffee production is also very water consuming.
No, this is killing me.
And we have water in Finland, so we can happily prepare beer, but we don't grow coffee here. So that can be a problem for some coffee producers, and we are heavy coffee users in Finland.
Yes.
Number 1 in the world. So maybe we should change to beer. Alcohol free, of course.
Okay, it was really good. Okay, so the message to take away with less coffee, more beer. No, I'm joking, of course. But yes, how about telling if we are answering any more answers to the question of if we are changing our habit? Okay, personally, I think for sure the first thing that I would like to do is to check my carbon footprint. This I'm curious. I know it will be a very bad news mostly because of the traveling, not only. But yeah, I'm very curious, and of course it's. I think that we are all doing already something by being more informed today. Then at least I am more informed than what I was before, and this I think it's a very important first step. So to learn more and then perhaps challenge ourselves a tiny little bit, not necessarily doing huge changes, but trying to think about small things that we all can do.
One thing that we didn't touch today is the compensation.
Oh my God.
But that's another.
In the sense of
No, I don't. But as we all know, that's one way of making good. That if you have to produce emissions, then you can compensate somehow, like plant a tree or something like that. And that is still
really something. You think this is actually a good point. Is it something that you think, even if it's a small thing, can contribute, or you would encourage people to do?
In principle, there are good compensation schemes, I think, but then there are also compensation schemes that do not convince me. I mean, they are.
For example,
Sorry, just about compensation, that it might psychologically be not a very good thing, because it's like paying for making bad decisions. So if I choose, justifying. So basically, if I choose to plant a tree for every airplane flight I take, I might take actually more flights, because I am kind of calming myself down that I can plant a tree.
And that brings us to the question of what should be the price of carbon when it is emitted. And almost every scientist believes that it's far, far too low price now that we are paying.
Actually, Kate Raworth, that you were using her model, she was warning about the marketplace and making ethical decision a market, and she was warning about the danger of putting a price on something. So basically, I think we have a better chance of having shame about overconsumption or having like social or cultural boundaries for carbon rather than a price for carbon.
Yes, I think it's different for individuals and then for like the economy. So in the macro economy there should be a price for carbon, because what we are basically doing now that we are over consuming the planet without paying, or we are not paying the right amount to actually cover the expenses that we cause. So for the macro...
Do you mean paying with money, or how do you pay?
Yeah, well, it would then impact us. If we paid the right price for, say, petrol, maybe that would be like 20 euros per liter. I'm just throwing a number. And that would probably have an impact.
Yeah.
If we think all the problems that are produced because of the emissions and everything, maybe 20 euros per liter would be the right, or 10 or something like that. So we are not paying the right amount because we are using the atmosphere as our dumping site and causing problems to ourselves.
Yes. Well, okay. I think that this is the right moment to conclude our Science Cafe. It's been really, really interesting, and I'm specifically happy because we all learned more, and I'm sure that this is, as I said before, the first step, and many of us will be trying in a small way to do something in our own small world, and of course education is always the first step. Before concluding, I want to say that the next Science Cafe will be on December 14th. The topic is not yet confirmed, so you will know it from the social media or all the other ways we communicate. Of course, I want to conclude by saying a huge thank to Jukka for this fantastic presentation, for his availability, and for all the questions answered. And thank you so much. Thanks. Please, you can stay if you want and ask more questions now.
I wonder what the carbon dioxide content of this room is now.